Hello everybody, welcome back to another glorious maths video. In this video I continue learning algebraic geometry, and I think today is going to be the last video on complex algebraic curves because at this point I'm kind of getting a little bit impatient. I just want to move on to varieties. I've skimmed through the entire text that I was going through, Complex Algebraic Curves by Robert Kerwan, and you know, I get the gist of basically what's being studied and whatnot, but now I just want to move on to varieties and then later schemes and all of that juicy stuff. So yeah, today I just wrap up kind of just some of the basics on complex algebraic curves, which will provide me with, hopefully, a little bit of motivation for the study of varieties, and then hopefully the study of varieties will provide motivation for studying schemes. So yeah, hopefully this has prepared me enough for learning algebraic geometry. In hindsight, perhaps it would have been wiser just to start with varieties, but you know, I'll see once I start learning about varieties whether, you know, learning about algebraic curves first has helped me at all, or, you know, if it was just kind of a useless endeavour. But you know, it was somewhat fun, you know, and yeah, you know, I still gotta do this video. I apologise for slight inactivity on the channel, although 2 weeks between videos is becoming sadly a regular occurrence. I will try to cut down on that. I will definitely try to cut down on that. Hopefully, you know, when I'm learning about varieties, you know, just kind of the work rate just shoots up, you know. But yeah, I do apologise for the, you know, this 2022, the start to 2022 has not been great so far, but hopefully it will just start ramping up come Easter. But you know, I'll make no promises, and even when I do make promises, they're not really promises at this point on this channel. But you know, okay, I'm getting a bit off topics or whatever. Just a little bit of notation to start off with, actually. Just so that I don't have to keep mentioning this. If I say C, I mean just a regular complex algebraic curve, like so. And these are called affine curves. So just normal sort of algebraic curves. And if I say C tilde, I mean a projective curve. So some sort of set that will look something like this. So just to get that notation out the way. And so we begin by reconsidering what we mean by projective space, and I don't mean kind of this set of equivalence classes, but I mean in terms of the complex numbers. So we're going to decompose it into two parts. We're going to compose it into the set of all x, y, z such that z is not equal to 0, so excluding the line at infinity, and then we're going to just kind of slap on a copy where z is equal to 0. And of course it is clear to see that it's just the union of those two things, but we'll see that those two sets are kind of special. So we'll call U the set of all x, y, z such that z is not equal to 0. And so z equals 0 is kind of known as the line at infinity. So this is basically just excluding the line at infinity. And what you might be expecting is true. It's very intuitive once I reveal this to you. You might not be expecting it, but it's quite an intuitive result, is that U is homeomorphic to the complex C2. I hesitate to call it the complex plane, of course, because that's just C, but so I'll just call it C2. And of course this isomorphism is very easy to define. So going from U to C2, it will be sending x, y, z to x over z, y over z, which of course is well defined since z is not equal to 0. And going the other way, we'll send some pair of complex points to x, y, 1. And you can check for yourself that that these two are inverses, which is very easy to check, and so U is homeomorphic to C2. So all that's left now of the projective plane, so of course we have C2, and then what, but okay, so it's C2, and then we have to attach to C2 the set of all points where Z is equal to 0, so that a line at infinity is what we have to attach. So I'm just going to leave this blank for now, and we'll call V the set of all x, y, 0. We'll call it like this. And this is very easily homeomorphic to P1, the projective line. All you have to do is just send the homeomorphism itself is just sending xy0 to xy, and obviously the other way around, and that's clearly a homeomorphism. I'm not even going to bother writing that down. And so the line at infinity is just the projective line. And so we get this neat little isomorphism, which when you break it down makes total sense, is that the projective plane is just C2, and with P1 a line at infinity attached, which is our intuition for the projective plane anyway. So this is just something to consider before we move on to studying, and this video is going to be about kind of comparing these two curves, trying to establish some sort of, correspondence between the two, and yeah. So okay, so, right, yeah, let me just do this. So firstly, we'll take a complex projective curve, and to get just a normal affine curve, all we're going to do is take the intersection of our complex projective curve with U, which we've established is homeomorphic to C2. So we'll just take a look at what this intersection really looks like, and we will hopefully get out just a normal complex affine curve. So if we take this intersection, we'll get the set of all x, y, z in P2 such that z is not equal to 0, and I forgot the symbol for and, it's either this or that, so I'm not going to risk it, I'm just going to write and p of x, y, z is equal to 0. Right, and this is simply equal to the set of all x, y, 1 in P2, such that p of x, y, 1 is equal to 0. And this is equal to the set of all x, y, just complex coordinates now, such that p of x, y, 1 is equal to 0. And so if we take a projective curve C tilde defined by p of x, y, z, then we can construct a affine curve by just removing the line at infinity, i.e. the affine curve defined by p of x, y, 1. And this should also be of degree d. It might be the case that it won't be of degree d if z is a factor of p of x, this polynomial, but I think that's true actually. If z, as long as z is not a polynomial, is not a factor of p of x, y, z, then this should also be of degree d. Don't quote me on that, but you know, it's not too important a detail. The important part is if we take any complex projective curve, we can pretty easily just construct a normal affine curve from it. So that's the takeaway there. What's slightly trickier is going the other way around. That is taking a complex projective curve and then, you know, creating an affine curve and then creating a projective curve. So we'll get cracking on that. So if we take some q of xy and we'll define it, we will make it not homogeneous, so we'll make it just the sum over all r plus s less than or equal to d of, let's say, a r s, so we'll just have some coefficients, and then we'll have y to the s, x to the r, for example. Then there is a way of making this homogeneous, and the way to do that is by defining a new slightly different polynomial. We'll define z to the d q of x over z y over z, and this will be, by definition, this will be the sum again over all s so it's equal to z d of a r s y to the s, x to the r, and then we just have z to the d minus r minus s. Now this polynomial here is homogeneous, and it's called the homogenization, I believe, of q. And so basically we have a homogeneous polynomial of degree d. And so the point of this is so that now we can study this, and hopefully we can study it as a projective curve. And so what we're going to do is we're going to take a look at where does the affine curve defined by this new thing here intersect with the line at infinity. That is when z equals 0. And the intersection of those two things is the set of all complex points such that the sum 0 less than or equal to r to d a r d minus r y to the d minus r x to the r equals 0. This is the intersection. And so by a lemma that we proved a while ago, we have that this sum right here, this sum between 0 and d of a r d minus r x to the r y to the d minus r, this can be factored as a product of linear terms, and so it's equal to product where I is between 1 and d of these linear terms, alpha I x plus beta I y. And so when these things here are 0, so the lines alpha I x plus beta I y equal to 0 are asymptotes. So basically the points at the line of infinity, so basically what this set here is the intersection of this with the line at infinity. And so when these things right here are 0, obviously this is 0, and by definition these are the asymptotes to our new complex projective curve. And so what's happened here is we kind of get a correspondence. So in MP2, so this is in C2. First in P1, these points are just kind of negative beta I, comma alpha I. These are just these points here. And in P2, these points are they are points in C tilde minus C. So these asymptotes right here, these are basically these points are added to the complex affine curve when you make it projective, kind of. And so the asymptotes are all of the things that are in C tilde but not in C. And of course, again, this is when you take a look at projective plane as C2 with a line at infinity attached. This again makes perfect sense. These are basically the zeros at the line of infinity. And so obviously these are going to be asymptotes in C2, and they're going to be points that are not on our normal affine curve, but they are on our projective curve. And so we have a sort of correspondence in that way. Another thing to add is and the lemma that I will not be proving or even stating, I'll just be kind of orally stating it just to wrap up this video, is that, again, if we study singular points and tangent lines, two concepts that we've studied in the last few videos, underneath these, underneath this correspondence I've been describing, you know, we do get the results we would expect. That is, you know, we have tangent lines, singular point on this curve here, if and only if it's on this curve here, and similarly, you have similar result for tangent lines. But I'll be leaving it up to you to prove that. And so yeah, this kind of concludes my little mini kind of complex algebraic curves part of the series. I mean, it was very short-lived. Only 4 videos long, but hopefully it's provided me with a little bit of insight into what I might be seeing. Hopefully it's provided me a little bit of motivation, and we'll see that in play when I make my next video, which will be on varieties. And yeah, I'm excited to learn about some varieties. So thank you guys for watching. Yeah, I'll see you in the next video. Hopefully it was all clear.
Bye.